Alright guys, so we left off on this problem. This is one of the multiple choice problems from one of the recent AP exams. And just as a reminder, you are not supposed to be using a calculator on the multiple choice section. So make sure as you are working through these multiple choice problems, whether on the practice pages or whether through the notes or on the test or quizzes or whatever, try to do them without a calculator. You will not be given a calculator or will not be allowed to have a calculator on the multiple choice section of the AP exam. So let's look at this problem and see what we can do. An iron ball is dropped, a hot iron ball is dropped into 200 gram sample of water initially at 50 degrees Celsius. If 8.4 kilojoules of heat is transferred from the ball to the water, what is the final temperature of the water, given that the specific heat of water is 4.2 joules per gram degree Celsius? Okay. So we know our equation is going to be Q equals MC delta T. We're not really being asked about the iron ball in any way, shape, or form. We're just given information about it, or told that we have it. So we're only going to be doing this for the water. Okay, so that makes our math a little bit easier. Q is the heat transferred, which in this case is the 8.4 kilojoules. Now the problem is, this is in joules. So we're going to have to convert that into joules, which remember is multiplying by 1,000. Which is going to give us 8,400 joules. Okay, our mass of water is 200. Our specific heat capacity, we're told, is 4.2. And notice this is simplified from what we've been using, and that's because it's multiple choice and you don't get a calculator. Okay, and then we are asked to find our change in temperature. So what I'm going to do is I'm actually just going to do delta T to find change in temperature first. Ignore the noise in the background. That is one of my dogs. I apologize. So let's go through and kind of do this. First thing I'm going to do is divide by the 4.2 mentally, just because I know that's going to be easier. I know 8.4, the original number, and 4.2 divide into 2. So 8.4 divided by 4.2 is 2, okay, because it's twice as big. And then, of course, because this is 1,000 times bigger than that, we're actually going to end up with 2,000 joules here. Okay, that's going to leave 200 over here times our change in temperature. Notice this math is a lot easier to work with. You also could have multiplied the 2 by the 4.2 and gotten our 8,400. Either way would have worked. Everybody's got kind of their own, not 8,400, sorry, 840. There we go. Each person may kind of have their own way of looking at it. I'm dividing by the 4.2 first. You can multiply and then divide either way. So then we're going to take this and divide it by the 2,000, or we'll take the 8,400 divided by the 840. Sorry, numbers are apparently hard to say right now. So when we divide this, we end up with 10 equals our delta T. Now the question comes, is this a positive change in temperature or a negative change in temperature? In other words, is the temperature of water increasing by 10 degrees or is it decreasing by 10 degrees? So notice here it's a hot iron ball, so we can assume the temperature is going to be above 50 degrees Celsius. Okay, that means energy is going to be transferred from the iron ball to the water, which means the temperature of the water is going to increase by this 10 degrees Celsius. So what we're going to be left with is 60 degrees Celsius, so our answer is going to be C. Okay. Now what I want you to do is stop the video for a second, and I want you to see if you can figure out this guy. This is, again, is from one of the new exams. It is a multiple choice. This one does not require a calculator in any way, shape, or form. It is purely logic. So pause the video and see what you come up with. Okay, let's check this out. A 10-gram cube of copper at temperature T1 is placed in an insulated cup containing 10 grams of water at temperature T2. If T1 is greater than T2, which of the following is true of the system when it has attained thermal equilibrium? Thermal equilibrium is just telling us that temperature is the same between the two species, meaning T3, the final temperature, is going to be equal for both the copper and the water. The specific heat for copper is 0.385, and the specific heat for water is 4.18. So let's break this down. First off, T1 is greater than T2. That means the temperature of the copper is going to be higher than the temperature of the water. So copper is going to have a higher temperature than water. That means energy is going to transfer from the copper to the water, meaning copper's temperature is going to decrease and water's temperature is going to increase until these two temperatures are equal to each other. Okay, so what all does that exactly mean? So energy is being transferred from copper to water. Well, how much energy is being transferred to the water compared to how much energy is water gaining? So energy cannot be created or destroyed, which means the energy coming from the copper is going to be equal to the energy going to the water, which means we have a negative energy leaving the copper, positive energy going to the water, meaning water is gaining. Keep in mind what we're actually looking at here is kinetic energy, due to the fact that it's just a temperature change. There's no intermolecular forces forming, meaning copper is not going to be interacting with the water in terms of intermolecular forces. We're not breaking intermolecular forces. We're not changing compounds. We strictly have kinetic energy. So very, very simple and straightforward. We'll look at one in a minute where we have a little bit more complexity, but this one's pretty straightforward. Next thing we have to recognize is the Q equals MC delta T equation is important here, knowing that, let's say, the Q of copper, so the mass of copper times the C of copper times the change in temperature of copper is going to be equal to the mass of water times the heat capacity of water times the change in temperature of water, okay? And the reason I'm setting it up like that is so we can kind of think through this, because if you look at these answers, what they're looking at is for you to recognize how much each temperature is changing. Is copper's temperature changing more than the temperature of water, or is water's changing more than copper, or is the amount of temperature changing the same, or can it not be determined from the information we're given, okay? So let's kind of break this down. First and foremost, we have to recognize that their masses are equal. So I'm going to kind of ignore this aspect right here. Okay, so the next thing I want to recognize is the specific heat capacity of copper is very, very small versus the specific heat capacity of water is very large. So check this out. The specific heat capacity of water is almost 10 times, actually it's more than 10 times bigger than the specific heat capacity of the copper. So that's very important here. So if these two statements have to be equal, what does that tell us? Well, that means the change in temperature for copper has to be much higher, and the change in temperature of water must be lower for these two values to equal each other. So think about it mathematically. If this is, let's say, 5, and the whole answer has to be, let's say, 20. I'm making up numbers here, so just kind of go with me here. Well, let's say our specific capacity is 5 here, and our specific heat capacity over here is 10. Well, what does that mean? That means this change in temperature has to be 4. This change in temperature has to be 2 for these two numbers to equal 20. So a higher temperature change, lower temperature change. So what does that mean? That means copper is going to change temperature more readily, or going to change more of a temperature than water is going to change. Meaning, let's say copper started at 100 degrees Celsius. It may end up at 30 degrees Celsius. Versus water started at 25 degrees Celsius, it may end up at 30 degrees Celsius, okay? So the water's not changing quite as much as the copper is. Now, why is that the case? It comes down to this idea of specific heat capacity values. Copper's got a significantly lower heat capacity. Well, what does heat capacity mean again? It's the amount of energy required to change the temperature of a substance by 1 degree Celsius. So if you've got a really low specific heat capacity, that means very little energy is needed to change the temperature by 1 degree. Versus water's got a very high specific heat capacity, so it takes a lot more energy to change its temperature by 1 degree. Okay, this is why you can hold a piece of metal in your hand and it's going to heat up to the temperature of your hand very quickly, versus if you hold the same amount of water in your hand, it's going to take a little bit longer to heat up. Okay, so the specific heat capacity makes a big difference. The lower the specific heat capacity, the easier it is to heat up. The larger the specific heat capacity, the harder it is to heat up. So both of these substances are gaining the same amount of energy, meaning their Q's are equal to each other, but that means the amount of energy gained by copper, or lost by copper in this case, is going to change the temperature quicker or more readily than the amount of water is going to. So if we go back through and look at our answers, copper is going to change more than the temperature of water. So that's going to be our thing. It's very tempting to answer C here because we see temperature is the same. Temperature is not the same thing as energy. It is related to the amount of kinetic energy that's lost and gained, or is related to the amount of kinetic energy involved but it's not actually related to the amount of energy lost or gained by a substance, because that's going to all depend on the specific heat capacity, mass, etc., and all the other fun stuff that goes into the physics. So be very careful. Temperature and energy are not the same thing. They are related to each other, but not the same thing. Okay, so very tempted to grab that one because we know our Q's are equal, but they're not actually the same thing here. Okay, let's go back and answer one of these questions that's a little bit more complicated, okay? And we'll end up having to do this over 2 videos, so I'm going to go through it first, talk about it, and then we'll let you solve it, and then we'll come back and do it on the next video. So let's say we mix 50 milliliters of 1 molar HCl at 25 degrees Celsius with 50 milliliters of 1 molar sodium hydroxide at 25 degrees Celsius in a calorimeter. After the reactants are mixed by stirring, the temperature is observed to increase to 31.9 degrees Celsius. We're told that the specific heat capacity of the solution is 4.18 joules per gram degree Celsius. Find the enthalpy of the reaction, enthalpy here being Q. Okay, so anytime we're looking at this type of situation where we're told there's a temperature change, we can automatically assume we're going to be dealing with Q, sorry, not G. Let me try that again. Q equals MC delta T. It's our only equation with change in temperature for this section. The next thing we have to recognize is this idea of system and surroundings. So when we talked about the metal ball, dropping it in water, in technicality, the water there is really the surrounding, and the metal ball is really the system. It's what's losing the energy. The metal ball is losing the energy, and the water is gaining it. And that's very simplified, because in technicality, the universe is technically the surroundings. So talking about that, where do we measure the temperature change? Can we put a thermometer on the metal and measure its temperature change? No, not very easily. So we measure the temperature change in the water and relate that back to the temperature change of the metal. Okay? And really all we have in that situation is kinetic energy transferred. In this case, we actually have a reaction occurring. So if we think about our reaction here, and yes, you still have to be able to write reactions. That has not gone away. We actually have chemical bonds forming here, okay? On top of that, we actually have intermolecular forces occurring here as well. So there's a lot going on. So this is a lot more complex than just the idea of dropping a piece of metal in water. What is our system? What is our surrounding? The whole thing is the system, meaning the water, meaning the chemicals, all of it is going to be the system. So again, a little bit more complex, and we're measuring the change in temperature of the water. And again, this gets a little bit hinky, so kind of bear with me for a second. The temperature of the water that's changing is almost like we're still measuring the surroundings of sorts. We're measuring that change in temperature of the water. The change in temperature of the water is due to the reaction of the solutions. Okay? Again, a little bit hinky, and we're going to work through this and kind of talk about it. But what I want you to kind of get from this is system and surroundings becomes a little bit ambiguous at points in times, and we have to be able to recognize that sometimes the water and the chemicals are part of both the system and the surrounding of sorts. How we're measuring it is where that has the ambiguity into it. But because water is part of the reaction here, and not just because it's a product, but because of intermolecular forces, we have to kind of include it in both circumstances, and recognizing that, oh, if water's temperature increased, that means the reaction is exothermic, and therefore it is losing energy. Okay, if that makes any sense. Or if the water's temperature decreased, which actually is increasing here because we're going from 25 to 31.9. But regardless, let's say the temperature is decreasing. Why is it decreasing? Well, because the reactants or the reaction is endothermic, and it's pulling energy in. Well, if the energy is being lost, where is it going? It's going into the surroundings or going into the water, which again is also part of the system. A little bit ambiguous there. If the water is losing temperature, where did that energy go? Well, it left the water and went into the reaction. Okay? So just kind of think about that for a second and just kind of digest that. It's a little bit weird, I know. What I want you to do is try to see what you can do with this problem. This is a little bit more complex. It's going to require a little bit of thought, and it's going to be a little bit more challenging than just putting a metal ball in water. But I want you to take a second, see what you can do. I'm not expecting perfection. I'm looking for an attempt. We'll come back and talk about it in just a second. Thanks, guys.